Welcome back to our machine design series. Today we are continuing our discussion of bearings by now discussing what might happen if we had a combination of radial and axial loading on a bearing. So I have taken the liberty of drawing a schematic for us before I started this video to show exactly what we're talking about here. So what we're dealing with is a rolling element bearing that is subjected to both a radial load, FR, which is the type of loading that we've been analyzing so far in our previous video where we talked about bearing life. Those were all radial loads. And now we want to understand what the effect of an axial or thrust load might be on the life of our bearing. So what we will do is we're going to define an equivalent radial load that includes the effect of this additional axial load, and we're going to call that FE for equivalent. And it is going to depend, of course, on the magnitude of our axial load, and it's also going to depend on whether we have the inner or the outer ring rotating. Excuse me, so to think about this, first consider that we could have a scenario where this outer ring of the bearing is fixed and the inner ring is the one that's rotating. Or we could have this scenario where this inner ring is fixed along with the shaft and this outer ring is the one that is rotating. And it has been observed that that has a significant effect on the fatigue life. So we're going to define a factor that helps us include that in our calculation. Okay, so to account for this difference in fatigue life, which it's been observed that bearings have a reduced fatigue life when the outer ring is the one that's rotating. And so when that is the case, we define this rotation factor, V equals 1.2. When the inner ring is rotating, V is just equal to 1. And now let's take these variables, Fe and V, that we've defined and plot them with the data that has been collected by researchers up to this point. And I'm just going to redraw an approximation of what this data looks like. On the x-axis, we're going to plot the ratio of our axial thrust load to V times FR. So this x-axis you can think of as the magnitude of the axial load that's acting on our bearing and shaft. And then on the y-axis, we'll plot the equivalent radial load over V times FR. So this is the relative magnitude of that equivalent radial load. And when we look at what the experimental data shows us, we get essentially a flat line for a while, and then at some point the data starts to follow this linear upward trend. So, of course, we can fit lines to this data. So if we fit a line to this side, we put that as a dotted line, and then let's fit a line, flat line here, where this flat line actually is just equal to 1. So what that tells you is that the magnitude of the axial load before we reach this point where things start to change, and I'm going to define this location as E. So when our ratio of FA over VFR is less than E, the axial thrust load essentially has no effect on our equivalent radial load. In other words, if our axial thrust load is small enough that it's in this area of our graph, it does not appear to have any effect on our equivalent radial load. But if our axial thrust load is big enough, then it does start to have some effect. And so what's going to be crucial in doing these calculations is first figuring out whether we are above or below this point that has been defined as lowercase e. And I don't know if this e has any particular name, but it is our cutoff point is what we'll refer to it as. So now the other thing we want to do is to go ahead and fit this straight line to an equation that has the form of y equals mx plus b. So if I do that, my y is fe over v times fr, right? And I let that equal to my slope, which is defined as capital Y, times x, which is fa over v fr, and then plus b, my intercept, which is just capital X, is how we've defined it. Okay, and so now we can multiply through by VFR and we can get an equation for our equivalent radial load that is equal to X times VFR plus Y times FA. And this is a very important equation, so we're going to box it. And we're also going to add subscripts to X and Y because we want to use this same equation whether we're on this side of E or this side of E. And we can do that by saying that when I is equal to 1, we're on this side of the line and we have values of X and Y that are just equal to 1 and 0, so that we eliminate this term where we're getting some effect from the axial thrust load. And then when we're on this side of the line, we'll have different values for X and Y that correspond to the y-intercept and the slope. So let's write that out mathematically. So here's a table that we can use to look up the values of X and Y that we will need depending on whether we are on the left or the right side of this graph. I'll try to move it up just so we can see everything all together. So if I look at the values of X and Y when I am on in this column of the table, this means that my ratio of FA over VFR is less than E, less than my cutoff, so I'm on this side of the graph. And when I'm there, my X, which is my y-intercept, is just equal to 1. Okay, there we go. And my slope, y1, is just equal to 0 because we have this flat line. When I'm on the other side of this chart where my ratio of FA over VFR is greater than E, so I'm over here and now our data is fitted to this line. Our intercept is always going to be 0.56, so there's really not too much work you need to do with that. And then y2 is going to depend on your value of FA over C0. So we need to be able to calculate FA over C0. And we haven't talked yet about exactly what C0 is. Up until this point, we have been talking about the basic dynamic load rating, which is sometimes called the C10 value. And that is the radial load that corresponds to 10% of a group of bearings failing at the manufacturer's rating life. If you want to hear more about that, check out our previous videos on bearing life. And now we are defining a basic static load rating that is C0. And this is the load that corresponds to a total permanent deformation in the raceway and rolling element at any contact point that is equal to about 0.01% of the diameter of the rolling element. So in other words, this is the static load that corresponds to a permanent deformation, a permanent yielding of the raceway and rolling element that is a certain percentage of the diameter of the rolling element. So let's write that out. Okay, and with this basic static load rating and the axial load that we desire for our bearing to be able to withstand, we can calculate this ratio of FA over C0. And once we do that, we can find the value of E that we need to use to compare to FA over VFR. And then we can use this chart, well, either this column or this column of data to calculate our equivalent radial load. With that, we can use the equations we developed in our previous video on bearing life to calculate our predicted life of the bearing. And in our next video, we will do an example walking through how you do that. Before we finish up here today, just some notes on exceptions to the rules that we've outlined here. For self-aligning bearings, V is going to be equal to 1, no matter whether the inner or outer ring rotates. And straight or cylindrical roller bearings are going to take little to no axial load, so Y will always be equal to 0. In other words, the straight and cylindrical roller bearings that don't take any axial load will not have an equivalent radial load that is affected by that axial or thrust load. All right, so that wraps it up for this video. I hope you found it helpful learning how to use an equivalent radial load to account for axial loading. It's an interesting process that relies more on correlations to experimental data than any kind of addition of forces that you've probably done before. We're not doing vector addition. We're not doing simple adding of the magnitudes of these forces. We're doing something entirely different that is really just a correlation from many, many experimental setups that researchers have done. So I hope you found this interesting and useful, and I hope to see you in the next one where we will work through a full example.